Hello everybody, welcome for our third tutorial on extremes and variability. And in this tutorial, we'll discuss the extreme value theory and do extreme value analyses with them. Again, first we'll introduce you to it and we'll discuss the different parameters of the extreme value distribution and show you what they do. And then we will draw a probability density function with them as well. So we're going to start with a new record, still from the build in the Netherlands. Sorry for that. That's a little bit of a bias of my own. But this time we're looking at maximum daily precipitation over about 100 years of data, so from 1920 to 22. Just as a start, you can see already some similarities here that we've done before. So we have most of the extreme values gathered around an average range, so between 30 and 40 millimeters per day, but then there are a bunch that are more extreme, that are a bit of an outlier. So the first thing we do, as we did before, is we made a histogram to look at our data, and from that we can compute our moments and fit the normal distribution. So we can compute, for example, the mean, the variance, and then you get the following graph, the following probability density function that represents a normal distribution. Now, at this point, when you look at this graph, perhaps pause the video for a moment and just look at what you see and what maybe strikes you, what you think about the fit of this data. Okay, hopefully you paused and you made some discussion, and hopefully you saw the following thing. If you look at the tails, you see that our probability density function is overestimating the lower half of the graph, so the lower tail, and underestimating the upper tail, the higher values in this case. So our normal distribution doesn't really provide a good fit, so we want to find maybe a different one. And this brings us to extreme value theory. Extreme value theory addresses the stochastic behavior of extreme events, so the random behavior or the random distribution of extreme events. That's what stochastic refers to. That is in principle very different from, for example, the normal distribution that doesn't really do that well. And that's why we really like it for climate change research, because we do a lot with extreme values, and this distribution fits better to those extreme events. So there are a bunch of different distributions that fit well to extreme events. For example, the Gumbel, Frechet, and Weibel distribution. However, we summarize those, or we bring those together in what we call the generalized extreme value distribution, the GEF. That's an acronym that we will see a bunch before. And below here on the slide, you find the mathematical representation of that distribution. We haven't really looked at that for the normal distribution. The normal distribution would have in total 2 parameters. The extreme or generalized extreme value distribution has 3. The shape, scale, and location parameter. The location parameter here represents sort of what the mean does for the normal distribution. So it tells us where the distribution is on the range of values that we have, on the range of precipitation values here. The scale is very similar to the variance or the standard deviation. It tells us sort of the width, how thick is the distribution, how far are values removed from the mean, in this case the location parameter. And then the shape is what to us is most interesting because it determines the thickness of the tails of our distribution. So the bigger the shape parameter, the thicker the tails get, the more extreme some of the values will be in our record. Let's look a little bit at what the different behaviors of all of those parameters. So here we have a distribution, a GEF distribution. You can already see it's a little bit different than normal distributions that we had seen before. The tails on the higher end of our precipitation is much thicker than before, the issue that we have with the normal distribution and our data. So here you have a location parameter of 30.5, a shape parameter of 7.5, and a scale of 0.027. What happens when we change our location parameter? So now we made it 40. You can see that the whole distribution barely changes in shape, it just shifts to higher values here. And that's because our shape and scale are still the same. So you barely see any change again in shape, but it's mostly just a shift in its location. Then we change the shape. So again, sort of that variant. You see that now our distribution gets wider. It gets a little bit, you could say, almost thicker. The peak also lowers because there's bigger chance of values around the mean. So the chance that we see the mean is reduced. And it also affects the extremes, as you can see. There's a higher chance of finding an extreme value. Now then, what does the shape parameter do? You have to be a little bit more, you have to look a little bit closer to the extreme to see the difference here, but you can see that it really affects the height of the distribution at its tail. So it's really the thickness that is of the tails that's changing here. And it's almost moving the distribution a little bit on its side. Those are the three different parameters and what they do. And their specific set, like each specific set gives a very different types of shape. And shapes that are more taking into account the skew, which was not something that the normal distribution did. So here I plotted them together on our data. I both fitted the distribution to the data that we had. And in blue, you see our GEF distribution, and in red, our normal distribution. So maybe again, pause the video and compare the two just to see like what you think about it, how they are different, and which one better represents. If you pause the video, then we can continue now. Of course, if you zoom in on the tails, you see quite a big difference. That's where our blue line, the GEV distribution, the generalized extreme value distribution, fits much better.